Good afternoon, everyone. Welcome to our session titled as High Performance Cloud Networking with Calico and VPP. My name is Shatakshi Mishra. I am working as a staff engineer at Marvell. I have 4+ years of experience in implementing programmable data planes with P4 and optimizing data plane offloads with data plane offloading with Kubernetes cloud native solutions like CNI, service mesh, and load balancers. Our team at Marvell focus on accelerated compute and hardware offloading, leveraging Octane platforms. We work extensively on data planes and protocol accelerations, and we have been looking into how accelerations can be integrated into Kubernetes. Now, CNI is actually an interesting use case because it comprises of almost all the networking function. And in this session, we're going to talk about Calico CNI and its integration with the VPP data plane. So some background story. As Kubernetes adoption grows in scale and complexity, its networking infrastructure must evolve to deliver both high performance and robust security. Traditional components like IP table and kubeproxy are widely adopted, widely used for a very long time, but it began to show significant limitations under large-scale workloads, particularly in terms of latency, throughput, and manageability of network policies. So to overcome these kinds of bottleneck, the community is increasingly trying to adopt some modern, faster, and programmable data planes for all the cloud-native environments. Now, these newer solutions focus on improving efficiency across critical networking function. One of the most promising one and the most famous name is eBPF, which is being used by many CNIs. But there is one more data plane option which has been explored, which is vector packet processing, a high performance user space data plane that is also well suited for hardware acceleration. So we're going to talk about VPP. Now there are a variety of container networking interfaces available, each supporting different kind of data plane technology. Among them, Calico stands out as one of the widely adopted CNI that integrates VPP as one of the data plane option. So Calico actually gives 4 or 5 different kinds of data plane options, and VPP is one of them, enabling high performance packet processing and advanced networking options. Calico also have components like network policy engine. It supports BGP-based routing, IP and IP, VXLAN, or native routing modes. Calico offers some n number of data planes, from which we're going to talk about 3 mostly used: IP tables, eBPF, and VPP. So IP tables is kind of the default Linux data plane, where all the processing happens in the kernel space, in the kernel networking stack. eBPF is the extended Berkeley packet filter, a powerful in-kernel packet processing engine which allows you to insert custom code inside your kernel layer. And then comes the VPP, Vector Packet Processor, a high-speed modular open-source software networking stack that allows you to do network packet processing on the user layer, user space. So now we will going to discuss about the 3 data plane option provided by Calico in detail. So this one is the IP tables. As you can see, all the traffic coming to the node goes to your kernel space, where routing and other network processing happens. And from there, traffic is being forwarded to the pods residing on that node. And that connection between the pods and the kernel is via wheat pair. Now, the second one and the mostly used one is the eBPF data plane. So Calico eBPF data plane attaches eBPF program to the TC hooks on each Calico interface, as well as your data and tunnel interfaces. This allows us to handle packet through through a fast path that bypasses the kernel layer. So in the diagram, you can see that only first packet reaches the kernel and uses the kernel networking stack. All other packet, all the rest of the traffic bypasses the kernel and go directly to the pod network namespace. The third one is the Calico with VPP data plane. So a VPP pod resides on the user space, which actually does all the networking, so that kernel level networking is not being utilized here. VPP actually takes your user's optimized plugin to take your interface, and so that VPP actually makes a kind of layer between the host and the network. VPP takes all the traffic that is coming to that node, process that traffic in user space, and then send that traffic to pods via two interfaces. Two options are available: TUN-tap interface and MEMIF interface. In the second diagram, it actually explains how VPP actually creates a layer between the network and the host. It takes your primary networking interface and create a similar mimic kind of a similar mirror copy of that interface, a tap interface on your host machine, so that now whatever traffic is coming, it's coming to the VPP because your main interface is with VPP. So all the whole kernel space, the whole kernel networking stack layer is being bypassed in this process. So Calico VPP supports two interface models. One is with MEMIF, one is with TUN-tap. With TUN-tap, when your packet, your traffic reaches the VPP pod by passing the kernel, after that when it has to reach the pod networking namespace, it goes via TUN-tap interfaces that actually created a TUN interface on the VPP pod and a socket API on the pod network namespace. Now this traffic between the VPP and the pod actually goes through kernel level because in the TUN-tap model. In the MEMIF model, you can even bypass this also. So this creates MEMIF model creates a MEMIF controller on the VPP pod side, which actually starts a VPP server. And then any VPP worker or client you can start in your pod network namespace, which actually takes traffic directly from the VPP pod. So in this level, no kernel interface is being required. So comparing all these three, if we talk about packet processing, IP tables and eBPF work at kernel mode, where Calico VPP is completely user level. Performance, IP tables give moderate performance, whereas eBPF and VPP, which totally bypass the kernel layer, and eBPF, which actually takes a fast path for the rest of the traffic, are giving high performance as compared to IP tables. That comes the latency. IP tables actually give more latency. eBPF and VPP give less latency. Encryption support, IP tables support IPSec with the help of Linux XFirm, and Calico eBPF does not have any native IPSec support, whereas VPP have IPSec native support, and also it is able to attach hardware offload. It's hardware offload capable. Then comes the networking feature. So Calico IP table supports basic net ACL. eBPF supports advanced features like XDP or DSR. DSR. And Calico VPP supports advanced networking like L2, L3, NET, ACL. Observability is limited in terms of IP tables because everything is happening at the kernel level. eBPF and VPP provides good observability as compared to IP tables with the help of eBPF map, or VPP gives VPP CLI in order to inspect everything. And then IP tables are actually compatible with all types of kernel. eBPF required modern kernel, and VPP required VPP integration to whatever underlying system you have. Now, deployment scenarios, which can be deployed where? So Calico IP tables can be deployed on legacy systems, any kernel. They are compatible with all kernel types and all simple systems. Where not to use, where you have high performance requirements, high performance cluster, where you need low latency, IP tables is not a very good option. eBPF, where modern kernels are there, where performance critical workloads are there, where you need programmability, where you need observability, you can use eBPF there. Where not to use, older kernels does not have support for eBPF, and also it doesn't have native support for IPSec, so yeah, while IPSec encryption is needed, eBPF is not a suitable option. And with VPP, where you need high throughput security with like in IPSec or any other, and where you need hardware-based acceleration, VPP is very suitable option there. But if you have lightweight or like resource constraints are there, VPP is not a valid option, and also not for simple setups. It has a complex structure. So yeah, my colleague Abed will be going to continue on VPP.
Thank you, Shatakshi. So I'm Abed. My team works on mainly data planes, accelerated data planes, security protocols, next generation transport protocols. We are heavily working on TLS and IPSec solutions, which are deployed in a lot of the infrastructure, whether it's 5G or enterprise. And VPP is part of that actually. So in the last 1 year, we have contributed heavily on VPP. And we have been one of the foremost open source contributors in VPP, where we have added support for Octeon and introduced a new device Octeon plugin. And I'm going to talk about that a bit. So how many of you here are aware of VPP? Okay, quite a group. So VPP is a fast user space networking stack, and it was open sourced in Cisco in 2016. It's very feature rich. It works, it has a very unique graph-based processing structure. And recently there has been a similar DPDK-based graph stack as well. But it's not as rich as VPP currently, but it's developing. And VPP has a highly pluggable structure where you can add a lot of new protocols as new graph nodes. You can add a lot of plugins for new features. It integrates very well with different third-party applications, and it's very well optimized for performance. So the way VPP utilizes hardware accelerations heavily. Like it uses the SIMD instructions of x86 of ARM. It uses the Neon instruction set. So most of the packet processing happens in batches. So it can happen in batches of like 4 to 256. So you can actually process 256 packet at each node at every time, right? And for that, it uses SIMD extensively. And it also integrates very well with hardware acceleration. It has a lot of options to plug engines, custom engines. And there is where we are going to talk about Octeon as well as what are the accelerations that we leverage for VPP. So there's an extensive network feature set in VPP. You can go through it on fd.io. It keeps on, there are a lot of features that keep on getting added. There are some features that are experimental, but the core L2, L3, L4 features are very well deployed, and they're already in production in lots of use cases. So broadly, VPP consists of like the infrastructure and VLib layer, which are kind of the core layers which manage your memory management, thread initializations, buffer managements. And it has a very good dispatcher and threading architecture where the nodes are actually scheduled. It has a very efficient scheduler, which does like sub-microsecond scheduling. And it's able to schedule lots of packets in bursts, right? The interesting part for this conversation would be VNet and the plugins. So VNet has all the L2 and L3, like all the routing related functionality, the IPSec functionality, and it has a lot of hooks to insert what you call new engines, let's say cryptographic engines and other things. And the plugins are where you can add new drivers. So what people are usually aware of is the DPDK driver. So the DPDK plugin is one of the oldest plugin, and there have been few talks about Calico and VPP earlier with the DPDK driver on Intel platforms. But recently, last year, there was a new device plugin that was introduced, which was able to create a native driver. Instead of using DPDK as an additional layer, now you can actually write native drivers. And there are already, RDMA is one native driver, you have Octeon as a native driver, and there are few other native drivers that are there in VPP now. And DevOcteon is fully upstreamed, and we are going to talk about DevOcteon. So the Calico work, Shatakshi will share benchmarks on Octeon in some time. So we have been able to run Octeon. So Octeon is an infrastructure processor. We call it an infrastructure processor. It's heavily deployed in a lot of the 5G infrastructure, a lot of the enterprise infrastructure around, and it has lots of use cases. So it primarily constitutes of ARM N2 Neoverse cores, and it also has some accelerators. So you have some lot of packet parsing accelerations, and then you have additional accelerations for flow ordering. You have classification modules. You have traffic management modules where you can actually set up QoS and scheduling policies. And then it also has some AI/ML inferencing engine, which I don't think there are any uses from the Calico perspective right now, but there can be a lot of interesting network forensic and visibility use cases for which it can be explored. And then it has lots of other virtualized accelerators for protocol and cryptography. So specifically, it is very good. It's one of the leading cryptographic engines there. And that's why IPSec and TLS performance are very relevant on Octeon. This is the typical packet flow in an Octeon processor. So when packet comes, it hits the ingress block where the packet gets parsed and classified. And then there is a scheduling option, or if for those who are aware of DPDK and VPP, you can also have a poll mode driver where you can actually poll for packets and schedule that in burst. So the packets are scheduled on the ARM cluster, and the ARM cores can submit that to other engines. Like it can submit it to, let's say, the AI/ML engine, or it can submit it to crypto engine, and then you can egress the packet. And these are highly efficient and high performance accelerators and cores. So it can be used for a wide variety of use cases. And generally the ARM, it's standard ARM core, so you can run any ARM application, right? The cryptographic and the protocol engines also support lots of other features. They can be used for other compute, and they can also be done inline. So before hitting the ARM core, you can have your packet decrypted and detunneled before it reaches the ARM core. So that is what we call inline processing. So where if you get an IPSec packet, the packet hits the engine first directly, and you can have the decryption done, you can have all the inner classification, inner reassembly, everything done, and then the packet is deposited to the ARM core. So that's one of the highly optimized use cases. But typically crypto, we call that as inline crypto offload, or not crypto, in fact it's advanced, it's inline protocol offload where the whole protocol is inline processed. And then you have the other option where you do look-aside crypto, where it actually hits the core submits an instruction to the crypto processor, and then it gets decrypted, and you get the results back on the core. So we'll be talking about the crypto mode today. Okay, some performance numbers that we can get on VPP. So it can do more than 13 Mbps forwarding per core, right? And that is like, and it scales very well. And for IPSec also, if you see, right, this is crypto numbers, which it can do up to 3 to 4 Mbps of IPSec. And that's like the highest that you can get right now on any core. This is where the acceleration is used. If you use inline acceleration, you can go even higher. But inline accelerations is integrating that in Calico is slightly tricky, and we will be attempting that at some stage. But right now, we are integrating the crypto offload with Calico. So The good thing is that Calico, by default, you can compile and you can run it. You can run Calico on ARM, and you can use the IP tables and eBPF, which Shatakshi explained earlier. For using the Octeon native plugin, which is even the DPDK plugin can be used directly. But to use the Octeon native plugin, we have some patches that we will be upstreaming in some time. So this is still a work in progress, and we have some initial numbers. So for Calico, we use the crypto accelerators that we are integrating. Currently, the numbers that we will show will be with the ARM v8. So ARM has a optimized crypto instruction set, which is called ARM v8 crypto. And that is also very well, it uses the SIMD instructions on ARM to optimize the crypto operations. And it is, you can say it's software optimized. The crypto acceleration is something that we'll be integrating later, and we will be hitting the numbers that I showed earlier on using just VPP. So we should be able to hit those numbers as well. So yeah, so where do we put all our software? I wanted to add this so that it's available. So so we have lots of data plane solutions and VPP solutions that we actually upload, and these are all open source. So you can search for Marvell DAO and you can see all these, and this, most of these solutions are well documented, and you can download and you can run it on Octeon. From a cloud and data center perspective, probably I'll cover it on the next slide. So what probably I think people mostly are using and are aware from a KubeCon perspective. So we have Nginx, and with lots of proxy examples, you can use it as a reverse proxy, and you can do TLS acceleration using our OpenSSL that is available on DAO. So this actually offloads all the crypto asynchronous and asymmetric and symmetric operations to the Octeon cryptographic accelerator. And the second one is something that is already it's also very well documented. So this is Cilium offload to Octeon. It's available on DAO. So this is something very novel where your complete CNI is offloaded to a DPU. And your pods, they can reside on a server, whereas your CNI and all your infrastructure workloads, as well as your IPSec workloads, can move to the DPU. And this is also well documented. And the third thing that we have, actually, I think this will be presented in subsequent KubeCon, is that where we are doing crypto offload to Octeon via Boring SL APIs. Other than that, the VPP numbers that I showed, this code is also available on DAO, and you can take a look at that. And there are some other machine learning and SNOT examples if those are of interest. Because we are in Hyderabad, so recently one of the things that I think the question that always comes is how can we get access to an Octeon? So we recently deployed some Octeon in a research facility at IIT Hyderabad. And if you actually have some compelling use case, you can reach out on this mail ID. And we'll try to see if we can have some setup for you as well. So this is mainly for next generation research on transport protocols and security protocols, and some Kubernetes examples as well. With that, I think Shatakshi will go over the benchmarks that we have done. So we are in the process of collecting more numbers, and we will be upstreaming this code also in a few months, including the crypto offload, both to Calico project as well as to DAO. So stay tuned on DAO for that.
So we performed some initial benchmarks with Calico on both x86-based setup and Octeon setups, covering IP tables, eBPF, VPP using DOP plugin on Octeon and DPDK plugin on x86-based setup. Yeah, like Abed said, final result will be published soon on the DAO GitHub repository. So this is like kind of the setup which we have used, where we have two nodes connected via 50G link. And we'll have traffic generator pod on one node, traffic receiver pod on another node, and Calico data plane will going to change. It will be it will be IP tables or VPP or eBPF. So this is the plane traffic benchmark. where traffic is being flowing from port to port, residing on two different nodes. So you can see that for IP tables, Marvell Octeon gives 27 Gbps, whereas the x86 based setup gives the 19.9 Gbps. For eBPF, Marvell Octeon gives 32.1 Gbps, and x86 based setup are 25.8 Gbps. And VPP, we used MEMIF interfaces instead of TUNTAP because MEMIF performs better. So for Marvell Octane, it gives 43.5 Gbps, and on x86 based setup, it gives 23.9 Gbps. Now we also perform the benchmark with IPSec. So these are ARM with crypto numbers. 8.77 on the Marvell system and 5.9 is like expected on the x86 based system, which are from a published website. We have also mentioned the website. So with crypto offload, it's expected that it can go up to 30 to 35 Gbps. So Calico with VPP, a high-performance networking solution. So it's a strong candidate for high-performance environment. VPP offers robust interfaces and also hardware offloads. Hardware accelerations are possible to attach with VPP. And TLS acceleration is achievable via OpenSSL hardware acceleration interface. Then it can also support some future use cases like PQC and machine learning inferencing. So,
Yeah, if there are any questions, feel free, we can answer them. Yeah, sure.
Is there a mic? Oh, yeah. So I admit I'm not familiar with MEMIF. I understand that if you have an application talking to, if you're using the TUNTAP interface, your application talks to the normal kernel socket API, and then VPP is reading those packets out using TUNTAP. So it works with any normal application out of the box. To make use of MEMIF and get that higher performance bypassing the kernel, does the application need special support in it?
Yes, actually. So MEMIF requires specific user space application that support the shared memory model. There is another interface that VPP supports, which is accelerated sockets, which can be, so you can use LD preload to use those sockets. And that is a faster alternative. It's not as fast as MEMIF, but it's a faster alternative to the kernel method, to the tap method that you would go otherwise.
Okay, that makes sense. So with that LD preload solution, you can still bypass the kernel.
You can still bypass.
Your app uses the normal socket API.
Yeah. The MEMIF is specifically if you can have some DPDK application or some VPP application, or you'll have to modify your application to add support for MEMIF, but it's very fast. Like it, yeah.
Thank you.
Yeah, hi. So this MEMIF is basically on huge pages?
Yes, it's shared memory, it's huge pages.
Yeah, same like DPDP.
Yeah,
DPD.
yeah, same.
Thanks.
Thanks for the good session. My question is specific to DPDK. In comparison with VPP, what are the challenges in DPDK for its adoption?
So, okay, DPDK as a data plane, so DPDK is more like building blocks to build data plane applications. And initial VPP was built on using DPDK as one of the input-output plugin. So if you actually use DPDK, you'll have to write your own networking stack. It does not have any ready. There is one grout and there are some other graph stack that is coming up in development, but that's not so feature rich. It does not have ACL, it does not have NAT, it does not have reassembly right now. So VPP is already a mature stack that way, a user space stack. And then VPP supports both. It supports a DPDK plugin. So if you actually want to use DPDK, you can use DPDK. But then that interface is very well abstracted. So on platforms that support native plugin, so native plugin, all the data structures are in VPP native data structure. So they are actually faster than the DPDK variation, where you still need some translation between the DPDK headers and the VLib headers. So the native ones are slightly higher performance in VPP. But if you actually write a complete DPDK application, but it would be too much work. Like you need to build the complete stack down up in DPDK.
Thank you.
Yeah, I hope that answers the question. On MEMIF, there is one other thing. There are some accelerations for MEMIF as well. Intel has something which they call DSA. So it's a hardware DMA engine which you can actually accelerate MEMIF using those DMA interfaces. We are also coming up with, we also have some DMA engines, and we are actually, it's not uploaded yet, it's not upstreamed yet, but we have some patches that we are going to push to VPP soon, which will have acceleration for MEMIF using the DMA engines. Any other questions? Okay, I think we are on time. All right, thank you. Thanks for attending the session.